So this will be a video about another representation called the induced representation. It's another representation that comes from having a set on which the group acts on. We've already seen a kind of representation that looks like this, that has a sort of structure where you have a set, which is the regular representation. In the regular representation, the set was actually the set of elements that eventually become the group. In this case here, the set will be the set of left cosets. Now this, I find, is one of the more difficult representations to understand, and so I'll try to make it as concrete as possible by working out an example. But let's first state things as usual abstractly, and then work things out concretely in the end. All right, so let G be a group, as always. And then H is contained in G, be a subgroup. And then V, a representation space of H. Remember, at least I'm being anal about the representation and the representation space. Which we know can turn out to be a KH module. The induced representation rho of G, denoted by ind H G on V, is a KG module whose underlying vector space is the direct sum sigma, which is in coset, and this acts on V. So in order to so when you're trying to trying to envision this space, we need a coset representatives. So there's also a multiplication operation. Multiplication operation defined as some element G acting on a coset will be defined as this. H in the subgroup, and tau being the unique left coset containing the element G times J sigma. So G sigma is one of these, is a coset representative in sigma. Let me just introduce some terminology. So terminology. Which is the left transversal set, which is elements sigma. This intersects all the cosets at exactly at exactly one element from each coset. So pictorially, what I mean by this is, let's say that we have a group G, which I represent by a box, and then we have the subgroup H, and then we have these cosets, and so on. We can form a set S, which, let's say, will have xi, xj, and so on. And you can see that the intersection of S and a coset, xi comes from this coset, and then there is no element in the set S that comes from this coset, apart from xi. Then xj comes from this coset, and there's no element in the set S which comes from this second coset. And then there'll be an element, let's say xk, that comes from another coset, xkh, and there'll be no other element that comes from this coset apart from xk. Okay, so this left transversal set will be very important. Okay. As you can see, this way of formulating the induced representation really works if I have a finite group. But a much more general way of studying what the induced representation is that does not depend on the group being finite is really that the induced representation is equal to the kg module tensor, the vector space, with the ring being the kh module. This is more general. So let's first explore what this means. So what does this mean? So again, we're doing the more abstract nonsense, and we're going to end this video with a concrete calculation. But let's first explain the much more general formulation. We'll first need a concept called the balanced product. So the ingredients will be R, which is a ring, and then we'll need a right R module, M, then we need a left R module, N, and then we need an abelian group. G. So we say that phi, which goes from the Cartesian product of M and N, and gives us an element in G, is an R balanced, or R middle linear, if for all M prime in N and N prime in N and R in the ring, the following hold. So phi acting on M n plus n prime is equal to Mn, sorry, this is phi, plus phi Mn prime, and M plus M prime, this is equal to M n plus M prime. In other words, it's bilinear in the arguments, and this is quite an important one. This is an R module. This is equal to M Rn. So the set of all such balanced products turns out to be, so denote as L R M N G, the set of all such balanced products. And if psi and phi are balanced products, phi plus psi and then minus phi, for example, are defined pointwise. This turns L R M N G into an abelian group. So why did we do all this? The reason we're doing all this is because what we want to understand is this tensor product. You see, this is a tensor product over a ring. And it turns out that in order to understand this tensor product, we need the notion of a balanced product. And really the unique thing about this balanced product is how it acts on elements that have been acted on by the ring. It's this property where the ring element comes in that makes it quite different, because there's so many structures that have bilinear maps, but it's that ring condition that really gives us what we're looking for. So now with this, we can define a tensor product over a ring. So now we have a tensor product over R, which is a ring. So for a ring R, a right R module, a left R module, the tensor product over R, which we shall denote as M tensor N, is an abelian group together with a balanced product. So the tensor symbol goes from M times N and takes us to this space. And in some sense, in some very general sense, it's the best kind of map we can have, and this has to do with the universal property of tensor products, which I will not go into. But let's go back to our induced representation. So back to induced representation. So remember, we're trying to understand the fact that the induced representation is this Kg module tensor, the vector space over this other Kh module. So how does this look like? We have the action of our group G. So G will act on, I suppose, let's have a notation for it. G will act on something that looks like this. So remember, this is our left transversal set. And this just, again, to remind you, is just picking coset representatives from one from each coset. And how does it act? This becomes I to n g tau, a representation of our subgroup H acting on Vi. So one thing to notice, so note condition phi m dot r n is equal to phi m r dot n. Well, how does that come in? So multiplying by gi, so multiplying gi by pi h, this just picks another coset representative. And thus gives us another pi h prime acting on n. So remember, pi is a representation that goes from h to gl v. So it really doesn't. So in the original equation here, we had the pi h acting on the vector space, but we could get the same result with the pi h acting on the g, and we'll just have a different pi h prime that acts on the, we could have the pi h acting on the v, or we could have the pi h acting on the g, and this just means that there would be a different pi h prime acting on the v, and the outcome would be the same. And so really what's happening is that we really do have a tensor product of our group algebra tensored with the v over the group subalgebra. So now for an example. Example, this will be very concrete. Example calculation. So let's pick Z4. So this is 0, 1, 2, 3. And with addition, I suppose I'll write it this way. And I'll pick Z2, again with addition. Okay, so how do we create our induced representation? So the first thing is pick cosets. I suppose calculate cosets is what I meant to say. Calculate our cosets. Okay, and our first coset is clearly going to be 0, 2, and our second coset is just 1, 3, and we only have 2 cosets to worry about. Once we've picked our coset, we can pick our left transversal set. So pick our left transversal set. This is really important. And I'm going to pick my left transversal set to be 0 and 1. So you can see that 0 is from sigma 1 and 1 is from sigma 2. And I called this before. This can be G1 and this can be G2. Okay. Once I've done that, we have to pick how our subgroup will act on a vector space. Okay, this is really important again. So pick a representation of Z2 on V. Now in my example, I'm going to pick V to be one-dimensional. So let's make V mv equal to 1. And we're going to say that 0 will act on V as e to the I 0, which is V, with V in the big V, and then 2 will act on V by e to the I pi V and that. So we have a group, we have a subgroup. The subgroup gives us cosets. From the coset we pick coset representatives, and then we pick a representation of the subgroup on a vector space. And I've picked a one-dimensional vector space. And the next thing is important, is the last step, which is to compute the action of G on the cosets. And this is really the meat of the problem. And I'm going to go through this step by step, and hopefully at a reasonable pace. So we'll pick the 0 element. So 0 is going to act by addition on the first coset, sigma times V, right? And this is going to be what? So remember our definition of the action of the group on the coset. So we had the group G, an element of the group G. It's going to act on the coset, and this is defined as another coset acting this, and whatever coset comes here is the one that has that has G times G sigma, where G sigma is an element of the coset. So this or maybe I can put it this way. So G times G sigma is an element of tau. And G sigma is the group element in sigma. Is in sigma. So remember that this is a representation that acts on cosets. So you have to bear that in mind, because otherwise all this will be very confusing. So we have 0 acting on the on this coset sigma 1 V. And remember, what we have to do is we have to write this as, we have to write the result as an element from the subgroup times a coset representative, a set, an element from our left transversal set. So we represent sigma 1v by a coset representative, which for us, remember, for us, it's 0. So if I want to do that calculation, it's going to have to be 0 plus 0, because 0 is a representative from sigma 1, and this is going to act on V. Okay. And then I have to write this result as some element this can be written as 0 plus sigma 1 acting on V, right? And then, sorry, let me put it this way. So we need to, so in this case it's trivial, but 0 can be written as simply 0 plus 0, where 0 is in the subgroup. And also tau in this case is still the subgroup. So both here in this case, what I'm trying to say is that tau is equal to sigma, because 0 is an element of tau and 0 is an element of sigma. So in this case here, it's trivial. We have 0 plus 0 acting on V. And then how does 0 act on V? We decided that 0 acting on V is going to be e to the I, 0 times V, which is V. So this is simply going to be 0 plus V, and then 0 is in the coset sigma 1. So this is sigma 1. Now let's do another calculation. 1 plus acting on this coset, and this is less trivial, although kind of trivial still. So the result of this, we're going to pick a coset representative for sigma 2, which we decided was 1. Remember, we decided up here that 1 will be our coset representative. And so when I want to do this calculation, it's going to be 1 plus 1, and this is going to act on V. And then the result is going to have to be written as a sum of something from the subgroup and another element in the group. So here this is 1, and 1 can be written as a coset representative plus, I'm doing 0. So we're still doing 0 acting on the second coset, and then this is 0. And I can write this as a left coset representative, plus an element in the subgroup, and this acts on that, and this would be 1 acting on V, which is sigma 2V. So remember, 0 acting on V is defined as V, and I have 1 times V, and 1 comes from the second coset, which is sigma 2. Now we can go to 1. So 1 is going to act again on the first coset. In order to do this calculation, we pick a coset representative. So this will be 1 plus a coset representative will be 0, and that will act on V. And how do we write that? We're going to have to write that as an addition of a coset representative plus an element in the subgroup. The coset representative is still going to be 1, and the subgroup element, which we decided is going to be 0. And so we have 0 will act on V as just V, and we're left with 1 acting on V, and this is 1 is in the coset sigma 2V. So the way 1 acts on this coset is that it gives me something from the second coset. And then we can do action of 1 onto the second coset. And in order to do this calculation, we get 1 plus a coset representative from sigma 2, which is 1. This will be on V. And then we use the representation of 1 that acts on V. So we need to write this result here, 1 plus 1, as the sum of a coset representative plus an element from our subgroup. Well, this can be written as 0 plus 2 acting on V. So remember, this is 2, and 2 should be written as an element from our subgroup plus a coset, an element from our left transversal set. But remember, 2 acting on V is minus V, and so we have and this is 0 is in sigma 1. Okay, and then the second last element, we have 2 acting on sigma 1 V. And so this is going to be calculated as 2 plus a coset represented from sigma 1. And this will be 0. And we have to write this as a coset representative from the left transversal set plus an element from our subgroup. So 2 can be written again as a left coset, an element from our left transversal set plus an element from our subgroup. And remember, 2 acts on V, according to our representation, as minus V. And so we get, again, sigma 1 V. 2 again will act on the second coset to give 2 plus 1. So remember, we pick an element from the left transversal set that represents the second coset, and that's 1 in our case. And then we have 3 here. So we need to write 3 as an addition of an element from our left transversal set plus an element from our subgroup. Well, an element from our left transversal set is 1. An element from our subgroup is 2. And then 2 is going to act on V to give minus V. And so we have 1 acting on minus V, and 1 comes from the second coset. And then lastly, we need to calculate the action of the third or the fourth group element, 3. 3 acting on the first coset is going to be, we pick 3 plus an element from our transversal set acting on V. And then we need to write 3 here as an element from our left transversal set plus an element from our subgroup. Well, an element from our left transversal set will be 1, an element from our subgroup will be 2. And then the 2 acts on V, and in our representation, 2 acting on V produces a minus V. And so we have 1 V. And then 1 is an element from our second coset. And then lastly, we have 3 plus sigma 2 V. And so we have 3 plus 1 V. And this is 4. But 4 is 0. So we need to write 0 as an element from our left transversal set plus an element from our subgroup. And this is going to be simply 0 plus 0, V. And 0 acting on V is just V. And so we have 0, and that's just sigma 1, V. So what does our representation look like? So 0, what it did was it took sigma 1 V to sigma 1 V, sigma 2 V to sigma 2 V, and so 0 is equal to 1, 0, identity. What did 1 do? Well, 1 took sigma 1 V to what? It took it to sigma 2 V. And it took sigma 2 V to minus sigma 1 V. And so 1 is 0, 1. And then what did 2 do? It took this coset to minus the same coset, and it took sigma 2 coset to minus sigma 2 coset. And so we have that 2 is equal to minus 1, 0, minus 1. And then 3 took the sigma 1 coset to minus 2 sigma minus sigma 2 coset, and it took sigma 2 V to sigma 1 V, and so 3 is equal to 0, 1, minus 1, 0. Okay, so just to emphasize, the steps are get your cosets, and from each coset make a transversal set. In other words, from each coset pick one and only one coset representative, and that's the one that you will use for your calculation. Once you've done that, you need to pick a representation of a subgroup on a vector space. I chose mine to be a one-dimensional representation space, and I chose this representation. And then you calculate the action of the group on the cosets. And remember that the induced representation is the action of the group on the set of cosets. So given that that's the case, what is the dimension of the induced representation? So the dimension of int h g, well, it's going to be the number of cosets in G times the dimension of V. In our example, is 2, and the dimension of V is 1, and so dim induced GH is equal to 2. See if you can understand why this is the case. So, just to give you a hint, the induced representation cares about the cosets, and for each coset we've picked a representation of H of dimension V. And that's the end of this video.